Hello everyone, today we are going to learn some important characteristics of a diode. These are the points we are going to discuss. At the instant of two materials are joined, the electrons and holes near the junction region will combine, resulting in lack of charge carriers near the junction. Or, we may say that the charge carriers are depleted from the junction region. So, this region of uncovered positive and negative ions is called as depletion region. Now, let us analyze the characteristics one by one. When there is no bias or zero bias, that is, VD equal to 0. Forward bias or VD greater than 0. Third is reverse bias, or VD less than 0. Under no applied voltage condition, holes, that is minority carrier in the N-type material near the junction will pass to the P-type material. Closer the minority carrier to the junction, the greater the attraction for the negative ions, and the less opposition to the positive ions in the depletion region of N-type material. Now the majority carriers, that is, electrons in the N-type material must overcome the attraction of positive ions layer in the N-type material, and also the shield of negative ions in the P-type material. However, the number of majority carriers in the N-type material is so large that a smaller number of them will have sufficient kinetic energy to pass through the depletion region in the P-type material. The same process occurs for the holes which are majority carrier in the P region, and they move towards the N-type material. It is found that these flow of charges are such that the resultant flow in either direction is zero. So, in the absence of any bias voltage, the net flow of charge in either direction of the diode is zero. The second case is forward bias, that is when VD is greater than 0. Here, the positive terminal of the battery is connected to the P-type material, and the negative terminal is connected to the N-type material as shown in figure 4.3. The forward bias potential will force the holes in the P-type material and electrons in the N-type material to recombine with the ions in the boundary of the depletion region. This will result in decrease of the depletion layer width as seen from this figure as compared to that of the zero bias case. The reduction in depletion layer width results in heavy majority carrier flow across the junction. So, under the influence of the E field, the electrons will start moving from N-type to P-type region, and holes start moving towards N region. As the applied bias increases, the depletion region gets thinner until a flood of electrons can pass through the junction. This will result in exponential rise in current as shown in this figure. From solid-state physics, the current equation can be written as equation 4.1, where Is is the reverse saturation current, small k equal to 11,600 divided by EDA, EDA equal to 1 for germanium and 2 for silicon. Tk is temperature in Kelvin scale. From equation 4.1 it is observed that, for positive values of Vd, the exponential term will grow quickly. The forward bias Vi characteristics is as shown in this figure. At Vd equal to 0, ID becomes 0 and we get the zero bias condition. Now, let us come to the reverse bias condition. Figure 4.4 shows that the positive terminal of the battery or voltage source is connected to the N-type material, and the negative terminal to the P-type material. The number of positive ions in the depletion region will increase because the positive potential will attract the electrons toward the anode. Similarly, the negative potential at the P-type material will attract the holes away from the depletion region. This results in widening of the depletion region. The depletion region will act as the potential barrier for the majority carriers in both sides, and the current due to majority carriers becomes zero. Point to be noted that the reverse bias potential will push the minority carriers in both sides to enter the junction. This will result in negligible minority carrier current of the order of microampere as shown by the arrow. This current is called the reverse saturation current, denoted by Is. The diode current is equal to minus Is. Now, Let us observe the forward and reverse bias region together for the silicon and germanium. Both of them do not show the same VI response. This is due to the internal body resistance and external contact resistance of the diode. Each contributes to additional voltage at same current level, which is determined by Ohm's law. Another point is that ID is in milliampere for positive values and in microampere for negative values. The forward threshold voltage for silicon is 0.7 volt and for germanium equal to 0.3 volt. Thank you for watching. Hope to see you in the next video.